The evolution of problem solving. From brute force to intelligent caching in the early days of computational problem solving, programmers relied heavily on brute force approaches that systematically explored every possible solution path. While effective for simple scenarios, these methods quickly became computationally prohibitive as problem complexity increased. Recognizing the inefficiencies inherent in redundant calculations, researchers developed techniques to store intermediate computation results. This breakthrough led to the emergence of memoization patterns, forming the foundation upon which dynamic programming was built. Memoization works by identifying overlapping subproblems in recursive solutions and caching their results for future reference. When applied judiciously, this technique can reduce exponential time complexities to polynomial levels. A prime example appears in the Fibonacci sequence calculation. Traditional recursive implementations suffer from O(2 to the power of n) time complexity due to repeated calculations of identical values. Implementing memoization reduces this to linear time performance. Recursive approach, Fn equals Fn1 plus Fn2, memoized version, stores previously calculated values in memory. Time complexity improvement reduces from O(2 to the power of n to O(n). Spatial trade-off requires additional memory proportional to input size. While memoization significantly improves performance, it requires careful identification of overlapping subproblems. Not all recursive functions benefit equally from this approach, necessitating thoughtful analysis before implementation. Foundational concepts, building blocks of dynamic programming. At its essence, dynamic programming relies on three fundamental components working in harmony: optimal substructure property, overlapping subproblems pattern, and efficient state transition mechanisms. These characteristics distinguish DP from other algorithm design paradigms. The optimal substructure principle states that an optimal solution to a given problem contains optimal solutions to its subproblems. This property allows us to build global optima incrementally from local optimal decisions. Overlapping subproblems refer to situations where the same subproblem recurs multiple times during execution. This repetition makes memoization particularly effective, as stored results avoid redundant recomputation efforts. State transitions form the mechanism connecting different subproblem instances. Carefully defined state representations enable systematic exploration of solution space without missing potential paths. These interconnected properties work together to transform complex problems into manageable building blocks. Recognizing these patterns becomes second nature after extensive practice with diverse problem sets. Implementation patterns. Top-down versus bottom-up approaches. Two primary implementation strategies exist for solving dynamic programming problems: top-down memoization and bottom-up tabulation. Both achieve similar outcomes but differ fundamentally in their approach to handling subproblems. The top-down method employs recursion augmented with memoization tables. It starts with the full problem instance and recursively decomposes it into smaller subproblems, storing computed results for later use. Bottom-up approaches construct solutions iteratively from smallest to largest subproblem sizes. This iterative strategy often provides better cache locality and predictable memory usage patterns compared to recursive implementations. Each approach has distinct advantages depending on the problem context. Recursive solutions may offer clearer conceptual mapping to original formulations, while iterative implementations typically yield better runtime performance. Choosing between these strategies involves evaluating factors like recursion depth limits, memory constraints, and desired code readability. Experienced practitioners develop intuition for selecting the best fit based on specific circumstances. Classic problems, illuminating key principles. Certain foundational problems serve as excellent teaching tools for understanding dynamic programming fundamentals. The knapsack problem, longest common subsequence, and matrix chain multiplication are among the most instructive examples. The 0 to 1 knapsack problem demonstrates optimal decision-making under capacity constraints. Solving it reveals how DP handles constrained optimization scenarios through smart state representation choices. Longest common subsequence, LCS, illustrates how DP manages string comparison tasks. By constructing a two-dimensional table, we efficiently find the longest matching sequence across two strings. Matrix chain multiplication showcases the power of parenthesization. Finding the optimal grouping order minimizes total multiplicative operations, demonstrating how DP solves combinatorial optimization challenges. These canonical problems highlight various aspects of DP design, including state definition, recurrence relations, and space-time trade-offs. Mastery comes from working extensively through such problems and variations thereof. Advanced techniques. Beyond basic implementation, as proficiency grows, practitioners encounter increasingly sophisticated dynamic programming techniques. Space optimizations, state compression, and alternative representations become vital tools in addressing more challenging problems. Space optimization techniques exploit observation that many DP problems require only limited previous state information. This enables reducing memory footprint from O(n) squared to O(n), maintaining correctness while improving efficiency. State compression applies when certain parameters have bounded ranges or exhibit regularity patterns. Encoding state variables cleverly allows representing larger state spaces compactly. Alternative representations include using bit manipulation or mathematical transformations to simplify state transitions. These creative approaches demonstrate the flexibility inherent in dynamic programming methodologies. Proficiency with these advanced techniques empowers developers to tackle more complex problems, pushing boundaries of what's computationally feasible with clever algorithm design choices. Optimization strategies. Tuning performance parameters while correctness remains paramount. Optimizing performance becomes crucial for handling large-scale inputs. Various tuning strategies help balance speed, memory usage, and scalability requirements. Time complexity improvements often involve redefining state definitions or reformulating recurrence relations. Sometimes simplifying the problem domain leads to significant efficiency gains. Memory management plays a critical role in DP implementations. Choosing between sparse and dense storage formats depends on expected access patterns and data distribution characteristics. Parallel processing opportunities sometimes emerge in independent subproblem contexts. Identifying parallelizable components can lead to substantial speedups in distributed computing environments. Profiling and benchmarking remain essential tools for identifying bottlenecks. Measuring actual runtime behavior helps determine whether theoretical asymptotic bounds match empirical observations. Pitfalls and best practices. Avoiding common mistakes. Novice implementers frequently fall prey to subtle errors when developing dynamic programming solutions. Recognizing common pitfalls prevents wasted effort and improves overall development efficiency. Failing to correctly identify base cases leads to incorrect results or infinite loops. Robust initialization procedures ensure accurate termination conditions for recursive calls. Incorrect state definitions produce invalid transitions between subproblems. Thoughtful consideration of parameter selection guarantees meaningful progress toward final solutions. Improper memoization strategies may lead to excessive memory consumption or missed optimization opportunities. Selecting the right data structures for caching determines both correctness and performance. Overlooking opportunity costs in decision-making introduces biases into the solution. Process. Rigorous evaluation of all viable options maintains optimality guarantees. Adhering to disciplined debugging practices becomes essential when diagnosing issues. Systematic testing with known test cases verifies both correctness and performance characteristics. Real-world applications. Beyond textbook exercises, dynamic programming finds application far beyond academic exercises. Its ability to solve optimization problems makes it invaluable across numerous domains, from bioinformatics to financial modeling. In genomics research, sequence alignment algorithms rely heavily on dynamic programming. Comparing DNA sequences enables discovery of genetic relationships and evolutionary histories. Financial institutions employ DP techniques in portfolio optimization. Balancing risk and return across asset classes requires precise modeling of interdependent investment choices. E-commerce platforms utilize recommendation systems powered by dynamic programming. Personalized product suggestions depend on analyzing vast consumer choice graphs efficiently. Transportation logistics benefits greatly from route optimization algorithms. Planning delivery routes, minimizing fuel consumption, and maximizing service coverage presents classic DP challenges. These real-world implementations underscore the versatility and practical impact of dynamic programming techniques across diverse industries and problem domains. Evolving paradigms. Contemporary developments in dynamic programming. The field continues to evolve with emerging trends shaping the direction of dynamic programming research and application. New developments challenge traditional assumptions and expand possibilities. Approximate dynamic programming addresses limitations in exact methods by relaxing precision requirements. This approach proves useful when dealing with high-dimensional state spaces. Reinforcement learning introduces probabilistic models to dynamic programming frameworks. Combining Markov decision processes with deep neural networks creates powerful adaptive systems. Distributed dynamic programming leverages cloud computing architectures to handle massive datasets. Parallel processing capabilities open new frontiers in big data analytics. Quantum dynamic programming represents an exciting frontier, exploring how quantum mechanics could revolutionize algorithm design in upcoming decades. Staying current with these developments equips practitioners to adapt to changing technological landscapes while contributing meaningfully to ongoing advancements in algorithmic innovation. Conclusion: embracing the power of dynamic programming. Dynamic programming offers a transformative perspective on problem solving, turning complex challenges into solvable components through intelligent decomposition and reuse strategies. Mastering this approach opens doors to tackling some of the most interesting algorithmic questions in computer science. To solidify your understanding, engage actively with dynamic programming problems through hands-on practice. Work through classic examples,